The Kepler laws are valid for all satellites and all celestial objects orbiting other celestial objects can be considered as satellites. The Earth is the Sun's satellite. The Moon is the Earth's satellite. So satellite is used only for artificial objects. It can be used for all objects. So Kepler created three laws. The first law says that all planets, for example, all planets orbiting the sun, the motions they do are actually elliptical. They're not perfect circles. And the difference between the ellipses and the circles is that the ellipses have two foci. They have two centers. When the two centers are made into one, we have the circle. So this is the shape of all motions. The orbits can be more or less elliptical, meaning closer to the shape of a circle or more oval. The elliptical shapes have two axes, the minor and the major axis. If the minor and the major are close, then the shape becomes more like a circular shape. If there's a huge difference between them, it looks more oval. So this is the first law. The second law has to do with the fact that we found that when the planets travel in elliptical orbits, when they're closer to, let's say, the sun, they move faster. Well, when they're away, they move slower. And as a result, the area that the radius, the line that connects the planet with the sun, okay, sweeps an area. And we found that at equal times, the areas that are getting swept are equal. So they sweep equal areas at equal times. The third law has math. So we found that for all celestial objects orbiting a certain object, just like the sun, let's say, the square of the period of their period of motion divided by the cube of the average distance from the sun is the same. So this fraction is the same for all planets, let's say, for all celestial objects rotating the sun, and they're all equal to 4 pi squared over the universal constant g times the mass of the sun. If we have objects orbiting another star, the fraction period squared over radius, average radius distance cubed, is given by 4 pi squared over g and the mass of that star. So we see that the relationship between the period and the average distance does not depend on the mass that is orbiting. It depends only on the mass that everything orbits around. So this is a very important concept. Now, for the satellites, all satellites, we said, and we're not talking about only the artificial, we're talking about all celestial objects, we can find how the speed it needs to have so it orbits at a certain height at a certain distance. Remember that the distances are always measured from the centers of the objects. For the satellites, meaning all celestial objects, I insist on that, we always start from the same fact, from the same equation. The equation that we use is that the gravitational force works as the centripetal force. So the force due to gravity is the centripetal force that makes the satellite orbit around another object. By doing so, we can find what the speed of a satellite should be at a certain distance r from the center of the planet, right? What we can see is that the speed of the satellite does not depend on its own mass. Just like the motion of the Earth does not depend on the mass of the Earth. It depends on the mass of the Sun. And the motion of the Moon does not depend on the mass of the Moon. It only depends on the mass of the Sun. So we come up with these formulas that help us be able to calculate what the speed of a satellite should be at a certain height, and of course the time for one rotation, the period of the satellite should be. Now, one more thing, usually we care for the so-called geosynchronous and geostationary satellites. Mostly for the geostationary satellites that we use a lot. So we know that these satellites should be at a certain altitude, so they have the same period with the Earth, which is 1 day, 24 hours, 86,400 seconds.